A steam engine sitting quietly in a rail yard looks like nothing more than a giant metal machine, but inside that iron shell, pressures are building that can turn the whole thing into a flying bomb in a matter of seconds. Today, we are going to find out exactly why that happens. Steam engines changed the world. There is no argument about that. From the moment James Watt refined the early designs in the late 1700s, these machines became the beating heart of the industrial age. They pulled trains across continents, powered factories that made goods for millions of people, drove ships across oceans, and pumped water out of mines so deep that no human hand could have managed it alone. For about 150 years, steam was everything. Steam was the future. But steam had a dark side that people in the 1800s knew very well. One that modern people have almost completely forgotten. These machines exploded, and when they did not just break down or catch fire. They detonated. They sent walls of iron flying through the air at the speed of cannon fire. They leveled buildings, killed dozens of people instantly, and left craters in the ground where a machine had been standing moments before. Newspaper headlines in the 1800s were absolutely full of these disasters. And the people who worked around boilers every single day understood that they were working next to something that could kill them without warning. To understand why steam engines exploded, you first need to understand what a steam engine actually is and what it is doing at every moment it runs. At its most basic level, a steam engine is a machine that turns water into steam and then uses that steam to push a piston back and forth. That motion is then converted into rotation, which can turn wheels, drive machinery, or power just about anything else you connect to it. The key ingredient is heat. You burn fuel, coal, wood, oil to heat water inside a large metal container called a boiler. As the water heats up, it begins to convert into steam. Steam takes up far more space than the liquid water it came from. And because it is trapped inside a sealed metal container, it builds pressure. That pressure is the force that makes the whole system work. The more pressure you have, the more power the engine produces. Now here is where things get dangerous. Pressure is energy. A boiler full of water heated to the right temperature and pressurized to the right level contains an enormous amount of stored energy, far more than most people standing next to one would ever realize. Water at high pressure and high temperature wants very badly to become low-pressure steam, to expand, to escape. The boiler is the only thing preventing that from happening. Every rivet, every seam, every inch of steel in that boiler shell is holding back a force that is always looking for a weak point. When it finds one, the result is catastrophic. The technical term for what happens when a boiler fails is a boiler explosion. But that word alone does not capture what is really going on. It is more accurately described as a rapid pressure vessel failure, combined with a phenomenon called boiling liquid expanding vapor explosion, or BLEVE. When the boiler shell ruptures, the pressure inside drops almost instantaneously to zero. All of the superheated water inside, which was only liquid because of the pressure keeping it in that state, suddenly finds itself free. It flashes into steam all at once. Every drop of water converts into vapor in a tiny fraction of a second. The volume of steam produced is hundreds of times greater than the volume of water that made it. That sudden, violent expansion is what produces the explosion. Not a chemical reaction, not burning fuel, but pure physics. Water becoming steam faster than the eye can see. The force released in this process is extraordinary. To give you a sense of scale, a boiler operating at just 100 pounds per square inch of pressure, which was considered moderate by 1800s, standards contains enough stored energy when fully loaded with water that its failure can produce an explosion, equivalent to several pounds of explosive. Large locomotive or marine boilers operating at higher pressures contained much more energy than that. When they let go, the results looked like a war zone. So what causes a boiler to fail in the first place? There are several answers to that question, and they come from different angles. Some from engineering, some from human behavior, some from the basic nature of materials under stress. The first and most straightforward cause is overpressure. Every boiler is designed to operate within a specific pressure range. The designers calculate how thick the metal walls need to be, how strong the rivets must be, and what kind of safety systems are required to keep the pressure from going above the safe limit. As long as the boiler operates within those parameters, it is safe. But if the pressure inside rises above what the structure can handle, the boiler will fail. The safety valve is supposed to prevent this. Safety valves are simple mechanical devices, essentially a plug that is held down by a calibrated spring or weight. When the pressure inside the boiler reaches the maximum safe level, the pressure lifts the plug, releases steam into the atmosphere and prevents the pressure from going any higher. In theory, a properly functioning safety valve makes overpressure impossible. In practice, safety valves failed in so many different ways that they became one of the leading contributors to boiler explosions throughout the steam age. Sometimes the valve was simply not strong enough for the boiler it was protecting. In the early days of steam, there were no standards, no regulations, and no engineering codes. Boilers and their safety systems were built by people who were learning as they went, and the valve that seemed right to a blacksmith building his first boiler might be completely inadequate for the pressures that boiler would develop. Sometimes the valve was the right size, but was set at the wrong pressure, calibrated to release at a point higher than the boiler could safely handle. But perhaps the most chilling cause of safety valve failure was deliberate human intervention. Throughout the 1800s, there are documented cases, many of them where the safety valve was intentionally disabled, weighted down, or tied shut by the people operating the machine. The reason was simple and deeply human. Pressure means power, and power means speed. A locomotive engineer who wanted to make up lost time on a schedule. A riverboat captain competing in an unofficial race against another vessel. A factory owner who needed more output from a machine. All of these people had practical incentives to squeeze more performance out of their boilers than the safety systems would normally allow. Tying down the safety valve was a quick and easy way to do that. It was also a death sentence for everyone nearby. But the connection between the action and the consequence was not always obvious. And in the competitive, money-driven world of industrial-age commerce, short-term thinking often won out over long-term safety. The second major cause of boiler explosions was low water level. And this one is particularly interesting because it is somewhat counterintuitive. You might think that a boiler full of water is more dangerous than one that is running low, because more water means more steam potential. But the opposite is true, and understanding why reveals something fundamental about how these machines worked. In a properly operating boiler, the water inside absorbs heat from the fire and carries it away through the process of converting to steam. The metal walls of the boiler are in constant contact with water on one side and fire on the other, and the water keeps those metal walls cool enough to maintain their structural integrity. Steel and iron, even the high-quality grades used in boiler construction, lose their strength when they get hot enough. As long as water is present to absorb the heat, the metal stays within safe temperature ranges and remains strong. But when the water level in a boiler drops too low, sections of the metal wall are exposed, no longer in contact with water on the inside. Those exposed sections heat up rapidly. The metal begins to soften. Its ability to contain pressure drops, and then, if cold water suddenly contacts that overheated metal, whether because a panicked operator tries to refill the boiler or simply because the water sloshes, the thermal shock can cause an immediate violent failure. There is another mechanism at work here too. When a low-water boiler has been running for a while, the exposed metal above the waterline becomes extremely hot. If the operator then adds water, that cold water can flash directly into steam the moment it contacts the superhot metal surfaces. The pressure spike this creates can be almost instantaneous, and if the boiler is already weakened, it will not survive. Water level management sounds simple, but in practice, it was a constant challenge. The gauges used to indicate water level in 1800s, boilers were not always reliable. They could become clogged with scale and sediment, give false readings, or simply be misread by tired or inattentive operators. Many explosions throughout the steam era happened because an operator genuinely believed the water level was adequate when it was not. Scale and sediment buildup was itself a serious problem, and it connects directly to the water level issue, while also introducing its own failure mode. When water is heated repeatedly over time, the minerals dissolved in it do not evaporate with the steam. They stay behind, and they gradually coat the inside surfaces of the boiler with a layer of hard, mineral-rich scale. This scale acts as an insulator. It prevents the water from doing its job of absorbing heat from the metal walls. With scale buildup, the metal behind the scale runs hotter than it should, even when the water level is normal. Over months and years of operation without proper maintenance, the scale can become thick enough to cause the metal to overheat and weaken to the point of failure. Regular maintenance, cleaning, and inspection could prevent this. But in the competitive commercial environment of the 1800s, taking a boiler out of service for maintenance was losing money. Many operators pushed their machines far beyond reasonable service intervals, and the scale built up silently until something gave way. Material failures were another category of cause, and these were particularly insidious because they could happen even when everything else was being done correctly. The iron and steel of the 1800s was not produced with the consistency and quality control that we take for granted today. Variations in composition, inclusions of impurities, inconsistencies in thickness, all of these could create hidden weak spots in a boiler shell that would not be visible from the outside and might not show up in any inspection. A rivet that looked perfectly solid might have a crack propagating through it from the moment it was installed. A section of plate that passed visual inspection might have internal voids that reduced its actual strength far below what its thickness suggested. The riveted construction used in boilers until welding became viable in the early 20th century had its own vulnerabilities. Riveted seams were inherently weaker than the surrounding plate. They were designed to be the point at which the structure could be assembled. And while they could be made strong enough for the intended pressures, they were frequently the location where failures began. The holes drilled for rivets created stress concentrations, points where the material was working harder than the areas around it. Under repeated cycles of pressurization and deep cracks could develop at these stress concentration points and spread over time, a process known as metal fatigue. That was not well understood scientifically until well into the steam age. Corrosion was another hidden enemy. Boilers are hot, wet, and frequently expose their metal surfaces to both water and steam in ways that promote rust and oxidation. The inside of a boiler wall could be corroding for years without anyone knowing it, because the corrosion was happening on the interior surface that could only be inspected during a full shutdown and internal examination. External surfaces were visible, but they were often covered in insulation or obscured by the structure of the locomotive or machine the boiler was installed in. The interaction between these different failure modes made boiler safety particularly difficult to manage. A boiler might be operating within its pressure rating, but if its walls had thinned due to corrosion, that rating was no longer valid. A boiler might have perfectly good water level indicators, but if the indicators were coated with scale and giving false readings, the operators were essentially flying blind. Problems compounded each other in ways that were difficult to anticipate and almost impossible to detect without systematic, rigorous inspection. The marine industry saw some of the most devastating boiler explosions of the steam era. Riverboats, ocean-going steamships, and working harbor vessels all relied on boilers that were subject to particular stresses. The vibration of the hull, the constant changes in load as cargo was taken on and discharged, the use of river water or even salt water in boilers not designed for it. All of these contributed to conditions that pushed marine boilers toward failure. The explosion of the Mississippi River steamboat Sultana in 1865 is one of the most deadly maritime disasters in American history, with estimates of over 1,700 people killed. The Sultana's boilers had been repaired hastily just before the voyage, and the repairs failed under the pressure of a heavily overloaded vessel. One boiler let go, and the chain reaction destroyed the entire boat in minutes. The railroad industry had its own catalog of disasters. Locomotive boilers operated under conditions of constant vibration, temperature cycling, and varying water quality depending on what was available along the route. Engineers and firemen working in the cab of a locomotive were positioned directly adjacent to the boiler and were frequently the first casualties when something went wrong. Many early railroad workers developed an almost fatalistic acceptance of boiler risk as simply part of the job, which itself contributed to the culture of ignoring warning signs, pushing machines beyond their safe limits. Stationary industrial boilers, the kind used in factories, mills, and pumping stations, had a different risk profile but were no less dangerous. They tended to be larger than locomotive boilers and to operate for longer, continuous periods. The consequences of a failure in a factory setting could be catastrophic for the building and everyone in it. A large stationary boiler explosion could collapse multiple floors of an industrial building and send debris through walls and roofs across a wide area. As the death toll from boiler explosions mounted through the mid-1800s, pressure began to build for some kind of systematic response. This was not a simple process. The industries that used steam boilers were powerful, and many of their operators resisted any attempt to impose external oversight on their machines. The argument was the familiar one: regulation stifles industry. Safety inspections are an intrusion, and the market will sort things out because operators have an obvious incentive to keep their workers alive. The market did not sort things out, because the people making decisions about boiler maintenance and operation were often not the people who would die if those decisions were wrong. The incentive structure was badly misaligned. A riverboat captain who raced another vessel and pushed his boilers too hard might win a bet and arrive at the next port faster. If the boilers held, he profited. If they did not, he might well die. But the passengers and deckhands who had no say in the decision died with him. The state of Massachusetts took the lead in the United States by establishing the first professional boiler inspection program in 1864, largely as a result of public outrage over a series of particularly deadly explosions. Other states followed slowly. The development of formal engineering standards, what eventually became the American Society of Mechanical Engineers, first published in 1914, represented a major turning point. For the first time, there were agreed-upon rules about how thick a boiler wall needed to be for a given pressure, how safety valves needed to be sized and tested, and what kinds of inspections needed to happen at what intervals. These codes and the inspection regimes that enforced them had a dramatic effect. Boiler explosions did not disappear immediately, but their frequency and severity declined significantly as standards were adopted and enforced. The engineering understanding of why boilers failed improved in parallel with the practical regulations. So the codes were not static. They evolved as the industry learned more about material behavior, fatigue, corrosion, and the complex interactions between different failure modes. Understanding why steam engines explode also means understanding something important about the physics of water and steam that was not fully grasped in the early steam age. The behavior of water near and above its boiling point is more complex than it might seem. At standard atmospheric pressure, water boils at 100 degrees Celsius, but under pressure, the boiling point rises. Water in a pressurized boiler can be heated far above 100 degrees while remaining liquid, because the pressure prevents it from boiling. This superheated liquid water contains a remarkable amount of energy. When the pressure suddenly disappears, as it does when a boiler ruptures, the water does not just slowly start to boil. It flashes, almost instantaneously, into steam. The volume expansion is roughly 1,700 times for water converting to steam at atmospheric pressure. And the speed at which this happens in a rupture event is essentially instantaneous on any human perceivable timescale. This flash vaporization is what distinguishes a boiler explosion from a simple mechanical failure. If you had a tank of cold water at high pressure and the tank ruptured, the result would be a mess, and possibly some injury from flying fragments. But it would not be an explosion in any conventional sense. The water would just spray out. But a tank of hot pressurized water that ruptures undergoes that sudden phase change, and the energy released by 500 or 1,000 gallons of superheated water, all flashing to steam, simultaneously, is what produces the explosive force. The boiler shell becomes a fragmentation projectile. The steam cloud propagates outward with tremendous force, and anything in the immediate vicinity, people, equipment, structures, is subjected to a blast wave that can travel for considerable distances. Boiler fragments found after major explosions were often discovered hundreds of feet from the explosion site. In some cases, large sections of boiler shell were thrown distances measured in city blocks. The 1905 Grover Shoe Factory explosion in Brockton, Massachusetts, sent debris more than a mile from the site. The blast collapsed multiple floors of the building and killed 58 people. Subsequent investigation found that the boiler had been operating with inadequate safety valves and had been running at pressures significantly above its design rating. The physics of scale and corrosion interact with these explosion dynamics in interesting ways. Scale does not just cause local overheating, it changes the heat transfer dynamics of the entire boiler system. A heavily scaled boiler requires more fuel to produce the same amount of steam because the scale is insulating the water from the heat. Operators who noticed that their boiler was becoming less efficient often responded by increasing the fire rate, putting in more fuel, running hotter, which meant that the already weakened metal behind the scale was being subjected to even higher temperatures. It was a feedback loop that could accelerate toward failure. One of the most instructive aspects of the history of boiler explosions is what it reveals about the gap between theoretical understanding and practical implementation. By the mid-1800s, the physics of steam pressure were reasonably well understood by trained engineers. People knew that overpressure was dangerous. They knew that low water was dangerous. They knew that scale was a problem. The science was there, but the knowledge did not automatically translate into safe practice, because the people operating the machines were not always trained engineers. The economic pressures pushing against safe operation were powerful. and the consequences of unsafe operation were sometimes not immediately visible. A boiler might run at excessive pressure for years without exploding, because it happened to have been well built, or because the periods of excess pressure were brief. An operator who did this repeatedly and got away with it learned the wrong lesson that the risk was acceptable, that the safety margin they were eating into did not actually matter. This kind of survivorship bias was a significant contributor to poor boiler safety culture throughout the steam era. The metallurgy of boiler construction also evolved significantly over the course of the steam age, and this evolution both enabled higher pressure operation and introduced new failure modes that took time to understand. Early boilers were made of wrought iron, which is relatively soft and ductile. It deforms before it fractures, giving some warning before catastrophic failure. As steel became available and affordable in the second half of the 1800s, boiler construction shifted to steel, which is stronger and allows for thinner, lighter boiler shells for the same pressure rating, but steel is also less forgiving than wrought iron in some respects. And understanding how to work with it, weld it, and inspect it required developing new knowledge and techniques. The shift from riveted to welded construction in the early 20th century was another major transition that brought its own challenges. Welded joints, done correctly, are actually stronger than riveted joints and eliminate the stress concentrations created by rivet holes. But welding done incorrectly with improper technique, wrong materials, or inadequate post-weld heat treatment can create internal flaws that are invisible to the naked eye and potentially more dangerous than anything a rivet would produce. The development of radiographic inspection, using X-rays to examine weld quality, was one of the key technological advances that made hypersure modern boiler operation genuinely safe. Modern steam systems, and there are plenty of them still in operation, in power plants, industrial facilities, and even some specialized applications operate at pressures that would have seemed impossibly extreme to the engineers of the 1800s. Boilers and power plants operate at pressures measured in thousands of pounds per square inch, and at temperatures that the iron and steel available in the 19th century could not even approach without melting. These systems work safely because of a complete set of engineering practices, materials, science, inspection protocols, and operational procedures that represent 200 years of accumulated learning, a significant portion of which was paid for in human lives during the steam age. The story of boiler explosions is, in a very real sense, the story of how industrial civilization learned to manage energy at scales that had never been attempted before. Each explosion was a data point, a piece of information about what goes wrong and why, and over time, that information was gathered, analyzed, and incorporated into engineering practice in a way that made the technology progressively safer. The process was slow, often resisted, and far too expensive in human terms, but it worked. The last major boiler explosion in a regulated industrial facility in the United States happened decades ago, and boiler operation today is one of the safest aspects of industrial infrastructure. What makes steam engines explode, then, is not any single factor but a combination of physics, materials, human behavior, and economics. The physics of high-pressure steam is inherently dangerous. There is no changing the fact that a boiler is a container of stored energy that will release that energy violently if containment fails. The materials question is about building containers strong enough, consistent enough, and durable enough to maintain that containment indefinitely. The human behavioral dimension is about operating those containers within their design limits, maintaining them properly, and not letting competitive pressure or laziness or short-term thinking override the fundamental requirements of safety. And the economic dimension is about creating systems of incentives and enforcement that ensure the human behavioral requirements are actually met, even when meeting them costs time and money in the short term. Every one of these elements had to come together for steam operation to become genuinely safe. And the history of boiler explosions is essentially the history of each element being understood, addressed, and integrated into the practice of the industry. Steam engines changed the world not just through what they built, but through what they destroyed and what we learned from that destruction. Every pressure vessel operating safely in the world today carries in its design the hard-earned lessons of every boiler that ever failed. That is how dangerous technology becomes, safe technology, not by avoiding the danger, but by understanding it completely, respecting it absolutely, and never forgetting what happens when you do not.